My name's Ravi Patel. I'm a scientist at Sandia National Labs in the US. And yeah, I'll be presenting error and variables modeling for operator learning. This is joint work with Inu Manikam and Mamakon Gulian, also at Sandia, as well as MK Lee at University of Alabama. So operator learning is essentially a type of regression where instead of trying to fit curves to pairs of points X and Y, like I'm showing on the left, we try to fit operators or mappings between functions with pairs of functions U and V. And as you can imagine, this operator learning is a useful tool for PDE modeling, because PDEs include operators as constituent parts. So one particular application we're interested in is in surrogate modeling, where you might know the fundamental physics, but it might be too computationally infeasible to simulate, or if you want to do uncertainty quantification or design optimization, you might not have the computational power to do so. So instead, you could train on first principles simulations, try to get a coarse grain model to use in UQ or design optimization, for example. And one place this is used is in digital twins. So here I'm showing an Earth scale digital twin where they try to combine satellite data with simulation data. And of course, trying to simulate an entire globe's environmental systems isn't computationally possible. So it's necessary to surrogate many of the Earth systems. And this has been done already for coastal and ocean dynamics. So this Fourier neural operator shown on the bottom has been shown to, it can emulate high fidelity simulations of these coastal and ocean dynamics coming from first principles. But it turns out that functional data is always noisy. So these are coming from signals, and signals always tend to be noisy. So just as an example, I'm showing terrestrial temperature measurements from satellite for various frequency bands. And for each one, you can see this characteristic stripe pattern that shows up. And we're going to always expect this kind of noise. And even when we can improve our measurement equipment, there will be a tendency to put them in noisier environments or run them at higher sampling rates. But it turns out that if you try to do operator learning with noisy data in the independent variables or the input to the operator, you'll end up with systematic bias for your estimate. So as an example, we'll try to recover the burgers operator here. So we want to recover the mapping between this blue function here on the left to this blue function here on the right, where the mapping is the burgers operator. But we'll corrupt both of these functions with noise shown in orange, and we'll try to infer the burgers operator only having access to these orange functions. And if we do ordinary least squares, so if we try to minimize the L2 error between the action of the operator and the data, on the input data, compared to the output data, we see this tendency to underpredict the action of the true operator. So shown in blue is the action of the true burgers operator on a noiseless test function. And the more noise you add in the independent variables, the more and more you'll underpredict the action of the true operator. And it turns out that standard neural network regularization techniques can't remove this bias. So I'm showing weight decay on the left and dropout on the right, and both of them still fail to recover the action of the true operator. We still underpredict the action of the true operator. So the goal of this project was to develop an error model that can correct for this bias. We assume that the underlying functions are smooth and that the data we're working with is those functions corrupted with white noise. So this type of bias has been dependent variables. The estimate for the slope is still unbiased, even when the standard deviation is higher. But now when you add noise to the independent variables, so if you add noise to X, the more noise you add, the more you'll underpredict the slope. And there's this formula here that tells you how much you'll underpredict the slope, depending on how much noise you have. So the more noise you have in X, the closer this gets to 0. So error and variable models are used to correct for this type of bias, and many have been proposed for standard regression. But it turns out that these tools are very narrowly tailored, so they have to be used for very specific problems. There's a couple of examples. Deming regression and total least squares regression can be used for linear regression if you have noise in the independent variables for linear regression. But you have to know the variance to use them. For an overview of a few different types of error and variable models, I recommend this thesis by Zwanzig. So we could generalize this type of attenuation bias we saw for scalar linear regression to linear regression of operators, discrete operators. So again, we're given noisy functions U and V, and we're trying to recover L for a noiseless function U hat. We'll assume that we're working in a finite dimensional space and that L is linear. If we have enough data such that the sample statistics converge, we can write down the ordinary least squares problem shown here, and its minimizer is shown here. So then if we look at the norm upper bound of L, we see that it decreases as we add more noise into U. So this is a type of attenuation bias. The more noise we have in U, the closer this norm upper bound gets to 0. So our approach for correcting this type of bias is shown here. Instead of just looking at the output of the operator, we model the joint error between the input and the output. So we look at the joint distribution of the input and output. So we'll assume that we can recover this U tilde, so a noiseless version of U from the noisy data U. And then given that, we'll look at the joint distribution between U tilde and U, as well as the action of the operator on the noiseless U versus the data, the output data. And we assume that this is this error is coming from a joint Gaussian distribution, where we have a variance for u and a different variance for v. So with this distribution, we could use maximum likelihood estimation to recover the operator L, the noiseless u, and the variances. However, u tilde, it's a function, so it's a very high dimensional object, and we don't want to optimize over this high dimensional thing. So instead, we'll introduce a filter G with parameters that we could optimize over instead. And in this work, we use a smooth spectral filter with a cutoff wave number kappa C and a bandwidth A. And then we could instead optimize over these parameters instead of u tilde. So next I'll go into the methods of parameterizing the operator. The first method is more physics. This is a method developed by us at Sandia. It was inspired by Fourier pseudospectral methods. The idea is to take your function u, pass that pointwise through a neural network H, then take the Fourier transform. Then you take the wave numbers kappa, pass that through a neural network G, take the product, and then Fourier transform back into visible space. So this type of parameterization includes a lot of operators found in PDE physics models. So heat equation, the Laplacian, Berger's operator, fractional Laplacian, convection operator. These are all captured by this type of parameterization. And we've previously used this method to learn colloidal dynamic, to learn the dynamics of this colloidal system, where we have Jose colloidal flow. We have varying particle concentrations, particle diameters, and we try to coarse grain molecular dynamic simulations of this system into 1D PDE. And the system we learn is able to generalize to unseen particle concentrations and particle diameters. The other method we look at is called deep ONet. This is a method coming out of George Karniadakis' group at Brown. And on the left, I'm showing one variant of this method called unstacked deep ONet. The idea is to take the function u, pass it through a neural network called the branch net, and then to evaluate the action of the operator at a point y, you pass y through it, a trunk net, and then take the dot product between the output of the two neural networks. So this type of parameterization actually has a universal approximation theorem. That's the benefit of this method. And on the right, I'm showing results from one variation of deep ONet called variational deep ONet, where the authors, they start with a crack tip location here, apply shear to this material, and then try to predict where the crack propagates through. And after training, the equation they find is able to generalize to unseen crack tip locations. So now we'll look at trying to recover the Berger's operator again, now with this area and variables model, where again, we're adding noise into u. We're adding more and more noise into the independent variable u. So on the left, I'm showing the result for ordinary least squares regression. And as before, we more and more underpredict the action of the true operator as we add noise into u. But then on the right side, we see that our method isn't actually robust. In certain cases, we do recover the action of the true Berger's operator better than we would have with ordinary least squares, but it has a tendency to overpredict or underpredict, so it's not very robust as shown. So if we look closer at what our minimization has found, we find that maximum likelihood estimation failed to find reasonable filters. So for these for these lower signal to noise ratios, um, our low pass filter actually doesn't do any filtering at all. It just returns the function as is. So we found we could improve robustness with this smoothness prior. So again, looking at the smooth spectral filter we work with, we place a prior on this cutoff wave number. So we want it to be within a certain range. So it doesn't just go to the maximum wave number and then the filter returns the input function as is unfiltered. And we do this by placing an approximation to the uniform distribution, which is sort of as weak a prior as we could come up with. We do that with this beta distribution, which is differentiable, so we could use gradient-based methods to do the optimization. So we use this beta distribution with shape parameters close to 1 with this delta. Then we could do maximum a posteriori estimation instead with this prior, where now we've introduced an extra hyperparameter, 2 extra hyperparameters, delta and beta. So with this method, we are able to robustly recover the action of the true operator, setting the hyperparameter beta to 10 for all of the signal to noise ratios we've tested. We're able to recover the Burgers operator. And even when we vary beta, we're able to recover the Burgers operator to a wide range of hyperparameters, only failing really at very high betas. Then we could look at how our smoothness prior has affected the filter. And we find that we're able to, now the recovered filter actually does low pass filtering for all of these signal to noise ratios. Okay, so next we look at how, next we try to recover the 2D Burgers operator as we did before. So we'll have this noise-free test function, and we apply the learned operator to it and compare it to the action of the true operator at the bottom here. And doing that for decreasing signal noise ratios. So if you use ordinary least squares as shown on the top, as you add more noise into U, the more you underpredict the true operator. Whereas if you use our error and variables model, we're able to recover the action of the true operator, even for very high amounts of noise. So next, I'll share some statistics. So on the left side, we compare ordinary least squares to error and variables, the relative L2 error on the test functions versus the data. So for very low signal to noise ratios, our error and variables model performs much better than the ordinary least squares. And eventually, as you add more signal, they both perform roughly equivalent. And then on the right, I'm showing how the error and variables model performs versus the number of samples you use. And of course, for very limited data, we're not able to recover the true operator, but as you add more data, we are able to recover the action of the true operator. Next, we look at how our error and variables model performs for different distributions of the smooth underlying input function. So for each row, we apply different transfer function to white noise to get our smooth underlying functions. And for each one, our error in variables model is able to recover the action of the true operator. Next, we have an extension of this to time-dependent PDEs. So we'll assume we're working with a first order in time PDE, this form, and we seek to infer the spatial operator on the right-hand side, L. But we're only given access to white noise corrupted solutions. So we can write the ordinary least squares loss as shown here, where we have this evolution operator P that takes U at a time 0 to U at a final time T. And the ordinary least squares loss would try to minimize the L2 error between that and the data at the final time. The error in variables model looks very similar as before. We'll look at the state at the time 0 and the state at the final time. And as before, we'll assume that the error here is distributed by Gaussian. And we compute the map as done previously. So here we'll try to infer the chaos equation, the Kuramada-Siva-Shinsky equation. So this is a chaotic PDE where you have nonlinear Berger's operator here. You have inverse diffusion that adds energy into the system, but that's counterbalanced by hyperdiffusion that takes that energy away. And on the top here, I show a test function. So we're trying to replicate this type of behavior. Since this is a chaotic system, we can't expect to recover this exact solution in an L2 sense. So instead, we compute the first few Lyapunov exponents. So on the left side down here, I compare ordinary least squares to error in variables for a variety of NTs. So these are so for the evolution operator, I use forward Euler. NT is the number of time steps used in the forward Euler. So for NT equals 2 and NT equals 4, both ordinary least squares and error in variables fail to recover the chaos equation. But for NT equals 8, both methods actually recover the chaos equation. So we find that actually our error in variables model isn't necessary to infer the chaos equation. You can actually get away with ordinary least squares. So we're still examining why this is the case. We believe we suspect that for learning operators that have some regularity, you don't actually need error in variables to recover them. So finally, to conclude, we find that failing to account for error in the independent variables leads to biased estimates in operator regression. In this work, we developed an error in variables model that can correct for this bias. And we've demonstrated that this type of error model works with more physics and deep net. For future work, we want to explore the full posterior distribution of operators. So besides just the map, we want to examine how other plausible operators could behave. Because in the case where you have very limited data, you might have many operators that fit the data well. So it makes sense to look at how those behave. So this effectively gives you a type of uncertainty quantification. So the action, the range of actions of operators sampled from this posterior will give error bars. So in this work, we've also looked at a very simple error model. We've just looked at additive white noise. So in future work, we might want to look at more complicated error models, so maybe multiplicative noise, or maybe spatially correlated noise. And we also want to relax the smoothness assumption as well. So since we use this low pass filter, we're assuming effectively that the input functions are all smooth. Many PDEs exhibit shocks. Those would break the smoothness assumption, so we want to consider that case as well. And then we also have our paper up on archive if you want to take a look as well. And with that, I'll conclude, and I'm happy to take any questions.